In this video lecture, I will technically construct and talk about the basics and fundamentals of Root-Locus in digital and discrete time control systems. Let's review our knowledge from Root-Locus on continuous time systems. We generally start with a fundamental block diagram structure where we have an open loop transfer function, and we try to analyze the location of the roots and poles of the system with a varying parameter of k, which is a proportional gain as constructed in this example. Okay, so this is k, and we are interested in what happens when k is element between 0 to infinity and how the roots and poles change with respect to change in k. Okay, so if you remember, y of s divided by r of s can be written as k times GOLS divided by 1 plus k times GOLS. Okay, so what is the root? Roots are the poles, or technically, which makes the denominator equal to 0. So we are interested in solving this equation. GOLS is equal to 0. Okay, so we can write GOLS as in this form, like 1 plus k times n of s divided by d of s is equal to 0. So for every k, there exists some s, for example, which is solves this equation, and they're called the poles of the system. Okay, and in 302, we learned rules such that we can derive the quality and quantitative structure of the Root-Locus paths with respect to gain k, technically, which solves this fundamental equation. Okay, now let's try to analyze the Root-Locus equation or Root-Locus framework in a discrete time control system. Okay, once we digitize the plant, okay, we can construct the similar problem like this, such as we have a discrete time gain k, okay, but we have a discrete time open loop transfer function which can consist of the plant, discretized plant, and the controller. Okay, so let's write the transfer function y of c divided by r of c, which is equal to k times GOLZ divided by 1 plus GOLZ. That's good. So what are the poles of the system is the ones which technically makes this equation equal to 0, or similarly, we can write it in this form, 1 plus k n of c divided by d of c is equal to 0. Okay, so what is the difference between these two equations? As you can see, the only difference is s is replaced with the z. Okay, so this implies that in order to draw the Root-Locus, we should use the same rules and same techniques because the fundamental equation is exactly the same between continuous time and discrete time systems. Okay, so it's good that we don't need to derive any rules, any procedures, any new thing to draw the Root-Locus of a fundamental discrete time system with respect to fundamental continuous time system. Okay, this is a good name, which means that you can technically use all of the examples, notes that you already know from the feedback systems course. Okay, so if you remember, in order to derive the rules of the Root-Locus, we rely on two conditions: magnitude condition and angle condition. I will not go into details, but I will just simply write the magnitude condition. Okay, so technically this equation is this: GOLZ is equal to -1. So this is the fundamental equation that we want to solve. So it has a magnitude and phase. Magnitude condition says that k times GOLZ is equal to 1. So we already assume that k is positive, so it's equal to k times GOLZ is equal to 1. And angle condition is the angle of this, which simply states that k times, okay, k doesn't have a phase, so we can just simply put it here. GOL, okay, so not for that. Okay, so that's good. Yes, exactly, it's true. So GOLZ, k times GOLZ phase should be equal to pi 2k plus 1, where k is an element of not real numbers, technically integers. Okay, k doesn't have a phase, so this is technically only the angle condition. I really recommend you to go over your notes from 302 and look at the Root-Locus notes from this course's lecture notes to remember the basics and fundamentals, how we can write the rules. Okay, so in today's lecture, I will review the resultant rules and we will solve some examples. Okay, good. So let's remember some of the rules. So first thing you should do is you should write your open loop transfer function in terms of poles and zeros like this. Okay, we have n many poles. As you can see, we have n many zeros. Okay, so number of zeros, number of zeros is equal to m, number of poles is equal to n. So this is m, this is n. Okay, so the first rule is root loci has n separate branches. What is n? Poles. You have like the number of poles equals to number of branches, which is technically obvious from main point of view, and this is true for causal systems. Okay, root locus or root loci starts from the poles of your transfer function. It will start from the poles. Okay, and you have n many branches. Okay, m of the branches, n minus m, and we know that m is less than or equal to m, terminate at the zeros of the opponent transfer function, and n minus m branches terminates at infinity, which are called implicit zeros of the opponent transfer function. Okay, good. So for example, if you have 3 poles, if you have 1, 0, okay, 1 pole will go to the 0, 2 poles will technically diverge to infinity. Okay, so another really important rule is the location of the root locus on the real axis. Okay, so what we do is we select the test point. Okay, if test point, which is real, a point on the real axis, has odd number of poles and zeros in its right, then we say that this is located on the root locus. Okay, let's solve an example. Okay, this is the transfer function. Okay, as you can see, we have 2 poles and 2 zeros. Okay, which is very good. So let's write them. Okay, this is that. So 1 pole, 1 0 is at 0. Okay, so 1 pole is at 2. This is 2. Okay, so we have a pole at 1. That's good. So this is 1. Okay, and we have a pole at minus 0.5. Okay, so it says that the root locus will start from the poles and they will go to the zeros or implicit zeros. So we have 2 poles and 2 zeros, which is obvious that we have only 2 branches. One is going to this and one is going to this. Okay, so let's look at this. Okay, so this region, I have 1, 0 on the right side. This is located in the Root-Locus. If I look at this point, I have 2 zeros and poles. So this is not located on the Root-Locus. Okay, so this is that. So let's check if it's correct or not. It should be correct. As you can see, it's correct. Okay, so in general, the most important part of the Root-Locus in a continuous time system is the imaginary axis. Okay, because we want all of the poles to be potentially in the open left half plane. But in a discrete time system, the region of stability is the unit circle. Okay, so we draw the unit circle. And for example, if you look at this pole is always stable, which is good. Okay, but this pole starts from a marginal stable point, which is z is equal to 1, and it will go to 2, which is unstable. So technically, this state is unstable for all possible values of k. Of course, in the case of the k is positive. Okay, that's good. So these are the, I think, the most important rules that you shouldn't miss in the exams. Okay, so let's go. So okay, so and sometimes we need to compute the gain at a specific point. Okay, and specifically we want to compute the gain when we technically reach the stability limits. For example, when the Root-Locus hits -1 and 1, which is the most important point. So what we do is we will simply use the magnitude condition. That's okay. So if it's on the real axis, it's equal to 1 over GLL divided by sigma, and it doesn't have to be on the real axis. We replace sigma with z, or which is the pole location, which is a complex number. We take the magnitude, and it will still give the magnitude of the gain associated with that pole. Okay, that's good. So let's solve an example. Okay, so we have 2 poles and 2 zeros, very similar. Is it same? No, it's not same. Okay, so I have 2 poles and 1 zero. Sorry, so it's even better. Okay, so let's draw unit circle. Okay, I have a 0 at z is equal to 1. Okay, that's good. I have a pole at the origin, and I have another pole at z is equal to 0.5. Let's draw the real axis. Okay, so this is included in the Root-Locus, of course, because I have odd number of zeros and poles in my right side, and this will pole will go to 0 in this direction. Okay, so this part is not included, and all negative real axis is included in the Root-Locus. Okay, so it means that this pole will go to minus infinity. Okay, so in a continuous time system, if a pole starts from 0 and go to minus infinity, we say that it starts from minus stable point and it will be always stable. But the point is, the region of stability is the unit circle. So here, this point is critical because it is the point where we change the stability condition. System becomes unstable. Okay, so what we need to do is we need to compute the gain at this point. Okay, so both in the mini projects and the exams, I always want you to find the gain where your Root-Locus crosses 1 and minus 1. Okay, so computation of the gain when your Root-Locus crosses a unit circle is important, but it's computational messy. So I want this sometimes, but I don't want it. It depends, but I always want the gain at this point and possibly at this point, of course, if it is valid. So what is the Root-Locus? K is equal to 1 over GOL minus 1. Okay, so it's kind of easy. Okay, so of course I need to take the magnitude. So it is equal to 1 divided by, okay, so let's clean that. I already know this. And I will draw it in the next part. Okay, this is good. So magnitude of, so, okay, so it is it's minus 1, okay. Minus 1, minus 1, okay, minus 1, minus 1, minus 0.5, that's good. It's equal to 1 over, I guess, so what is it? Okay, 2, doesn't matter. And this is, I guess, 1.5, is it? I think so, it's 1.5. It should be something like that. And it is equal to 1.5 divided by 2, which is equal to 0.75. Let's check if it's correct or not. It should be, yes, it's true. As you can see, k is equal to 3 over 4. Okay, and this is the Root-Locus, as you can see. So we already know that it's super easy to draw the Root-Locus by MATLAB, and as I told you, I allow you to use MATLAB in the midterms, and for that reason, I will need to come up with some intelligent ways of asking questions about Root-Locus. Okay, good. But it's still important to draw Root-Locus by hand to better understand its meaning. Good. Okay, so what are the other important rules? Okay, asymptotes. Good. So here, we actually have an asymptote because we have 2 poles and 1, 0. But in this case, asymptote is trivial because we have 1 asymptote. Angle of the asymptote is equal to 180 degrees, and of course, which is associated with the pole that goes to minus infinity. Okay, so if you have 1 asymptote, you don't need to do any computations. Okay, so please save some time and avoid unnecessary computations associated with the Root-Locus. Okay, asymptote starts to be meaningful when we have like 2, 3, 4, and it goes like that. Okay, so what we need to do is use the formulas which we derive using angle and magnetic condition, technically angle condition, and we make some assumptions and approximations. You should look at your lecture notes. Okay, so technically it's very simple. Okay, so angle of asymptote is this. Okay, pi. Okay, multiply 2k plus 1, and k is a number from 1 to n minus 1 divided by n minus m. Okay, it will give the angle of the asymptote for each asymptote. Okay, and we also want to compute the real axis intercept of the asymptotes, okay, which is sigma a, and we simply sum the poles minus sum of the zeros divided by n minus m. Let's solve an example on that. Okay, so do we have an example? Yes, we have an example. Okay, so it's a very simple example, which should be enough for illustrating the idea. Okay, so I have a pole at 1 and pole at 0, and this is my region of stability. Okay, so let's start with the real axis. That's good. Okay, real axis is here. Okay, I have 2 poles. They are approaching each other in this direction. Okay, good. So I have 2 poles, no 0, which means that I have 2 asymptotes. Okay, so if you have 2 asymptotes, it's obvious that if you plug the formula, they will be 90 degrees and minus 90 degrees. Okay, these are the asymptotes. Okay, so if you plug the formula, because pi is pi and minus m is 2, okay, if you plug it, it is 90 and minus 90 degrees, or pi over 2 pi. Okay, good. So I already know that it is like, it's vertical. One is going in this direction and other one is going in this direction. So let's compute the intercept. They intersect. Okay, so sigma a is equal to number of the summation of poles is equal to 1, right? 1, that's it. Okay, that's good. So minus 0, it's 2, it's equal to 1 over 2. That's great. It's at 1 over 2. Okay, it's 2. So we have asymptotes. One is going in this direction, one is going in this direction. Okay, so in this problem, as you can see, I put asymptote intersection and breakaway point at the same instant. Okay, so because I know that this is breakaway point, okay, which is also equal to 0.5. Okay, when you have two poles, it's always the case. Breakaway point is equal to the intercept. Okay, but it may not be true for, of course, higher order cases where we have 3 asymptotes or 4 asymptotes. So it should be important to analyze breakaway and break-in points. So what are they? Okay, so as you can see, this is the result. Of course, okay, it's also a good point. I generally want you to compute the gain associated with breakaway points. You don't need to, of course, compute the gain associated with intercept, but this is also a breakaway point. It really qualitatively changes the behavior, because here, until you hit the breakaway point, you have two real poles. They are both positive, which means that there is no oscillations. And after that, you start observing oscillations, and of course, there's overshoot and other kind of details. And at some point, you became unstable. Okay, and computation of this by hand is much messier than computation of imaginary axis crossing in continuous time systems. Okay, that's good. So let's go to breakaway and break-in points. Okay, so we have break-in breakaway points in some Root-Locus diagrams. Okay, it generally happens when you have two poles approaching each other, or sometimes you have two zeros, okay, where poles are just leaving at break-in point. Okay, so there are three ways of computing breakaway points. Okay, you have G O F Z. Okay, and we know that breakaway points exist on the real axis, so sigma is real. Okay, so both formulas will give you an equation where you can find the break-in points. Okay, so derivative of G of sigma with respect to sigma, or derivative of the 1 over G of sigma with respect to sigma, or if you write n of c and d of c, which is numerator and denominator, if you equate this equation to 0, you will get the break-in points. Okay, so we already write the rules and technically prove this in 302. I will not do it here, but I will just solve an example. Okay, good. So let's solve an example. Very good. So as you can see, what I have, 2 poles, 1, 0. Okay, good. 2 poles, 1, 0. So let's start with that. So 1, very good. So it is 0. Okay, 0.5 and 1. That's great, right? Okay, that's nice. So I know that this is on the Root-Locus and this is on the Root-Locus, right? Okay, that's great. Okay, so I forget the 0. Okay, so this should be 0. Sorry for the inconvenience. That's great. Okay, so these two poles are approaching each other. Okay, that's good. So they will need to break away, right? Because they should go to a 0 or an asymptote. So what I will do, they will just break away. Okay, like this. Okay, and this is in the Root-Locus. So some pole should go to 0 and some pole should go to minus infinity. So what they will do is they will meet at somewhere here. Okay, so we don't know where. If it can be inside the unit circle, it can be outside the unit circle. Okay, so this is minus 1. Okay, this is minus 0. No, it's plus 1. It's plus 0.5. So we don't know exactly the shape. So what we need to do is we need to label this point, which is a breakaway point. Of course, we also need to compute this breakaway point, and then we need to also compute the associated gains. Okay, let's do that. Okay, so let's remember this, and I will clean that to compute the breakaway and break-even points. Okay, good. So I will use this formula, but using n of them is fine. Okay, so what is d of sigma is equal to, let's say a. Let's simplify it because writing sigma is hard. Okay, so d of a is equal to a minus 0.5. Okay, and this is equal to a minus 1. That's good. So d of a is equal to a squared. That's good. So I think minus 1.5a plus 0.5. I think it's correct. Okay, I'll also open an October MATLAB to compute. Okay, this is the a. I know that. So what I need to also, I need to compute the, okay, derivative of the dA with respect to a. Okay, take the derivative of this. This is equal to 2a minus 1.5. Okay, so I need both of them in order to compute the breakaway points. Okay, good. I have two equations. So what is n a? It's equal to a. Okay, what is derivative of n a with respect to a is equal to 1. That's great. So it's easy. So let's write this second equation. Okay. Okay, derivative of n is equal to 1. So I need to use that. A squared minus 1 point of a plus 0.5 minus, okay, so derivative of this with multiply with a, so it's equal to 2a squared minus 1.5a should be equal to 0. Let's simplify it. Okay, minus a squared. Okay, that's good. I think it's not that hard. Okay, so I think I will, these are canceled each other, which is great, plus 0.5x equal to 0. So a squared is equal to 0.5. So a is equal to plus minus, okay, that should be not correct. I think it's correct. There is no problem. Okay, it's plus minus. Okay, it's correct. Plus minus square root of 5. Okay, so what is square root of 5? Let's check. It is equal to 0.5. 0.5. Okay, 0.007. Okay, so I computed A. Okay, so what is A? A is breakaway point. So it means that I have two breakaway points. They are symmetrically distributed with respect to the real axis. Okay, so if I go to the result, I will see that, okay, so I have two breakaway points. Okay, this is at 0.07 and this is at minus 0.0707, which is equal to square root of y divided by 2, square root of divided by 2. Everything is correct. The next step is, what you should do is just use the magnetic computation to compute k's here. Okay, so let's analyze this Root-Locus to get a better idea of what's happening. Okay, so when k is equal to 0, we start at a marginal stable point because we have a one pole at z is equal to 1. Okay, so as soon as we increase k from a positive value, it becomes stable. We have two poles on the real axis, so there is no oscillation. It's an overdamped system. Okay, that's nice. So at some point, they meet each other when k is equal to 0.08 or 0.09, where your poles are located at square root of 2 divided by 2, okay, on the real axis. And then they will break away, like, and they will move away from the real axis. They will be complex conjugate, and as soon as they become complex conjugate, it will be oscillatory. Okay, so then after that, they will start, they will meet at the negative real axis, where k is equal to minus square root of 2 by 2 or 0.7, and k is equal to 2.9. Okay, so it's a larger gain k, of course. Okay, but here, okay, different from continuous time system, they are both real but negative. And negative pole means that there will be some sort of oscillations. This oscillation is different from the like smooth continuous oscillations that we observe in continuous systems. That these are more like tick-tock like oscillations, because it's like at some point it's positive, negative, negative. They are extreme oscillations. Okay, it's one of the important things that you should be careful about discrete time systems. A discrete time system is non-oscillatory only if all of the poles are on the positive real axis. Okay, And at some point, what happens is one pole will go to 0, one pole will go to 0, okay? So when k is equal to 3, as you can see from this example, and it's really easy to compute k is equal to 3, your pole, one of the poles is equal to -1, which means that your system is now unstable. For this system, for bibo stability, we need to have this condition, k should be element of 0 to 3. Of course, we are limiting to positive k values. Okay, that's good. So as you can see, drawing Root-Locus, we use the same rules in continuous time systems. The only difference is the meaning of Root-Locus is different in discrete time systems, both in terms of stability and behavior oscillations. But the computation, like drawing techniques, procedures, they're all same. Okay, so what you only need to do is solve some examples that are specific discrete time systems and try to understand the meaning of when we break the stability, when we break the oscillatory conditions, and try to get an idea about the discrete time system performance.